Hello guys, today we will be discussing another topic in steel design, which is the behavior of compression members, or generally known as columns. So for the compression member, the failure consideration is more focused on what you call buckling. Okay? So as you can see here in this figure, the column bends either way um, on the two axes, and it is actually very similar to a bending behavior, but the only difference is the load concerned is actually an actual load normally applied on the center of the axis, the longitudinal axis of the member. So unlike bending in flexure, so bending is more concerned on transverse loadings. So in buckling, loads are actually axial. Okay, so if you have here a beam for bending, the loads are normally placed perpendicular to the axis of the member. So this is what you call now a transversal or transverse loading. So the basic column strength assumptions are here enumerated and categorized depending on the conditions set forth. As to the material, the assumption is that your compressive properties, specifically the stress strain property, is uniform throughout the section, and there is no initial or internal residual stress that exists due to cooling, after rolling, and welding. So this residual stress will be discussed to you later. Okay. So with regard to shape and condition, so we have here assumptions made to simplify the derivation of the equations we need to come up with the analysis of columns. So it is assumed that the column is perfectly straight and prismatic. The load resultant acts at the centroidal axis of the member until it begins to bend. Okay, sometimes loads cannot be perfectly applied on the centroidal axis, and the end conditions must always be determinate so that a definite equivalent beam length KL may be established. Okay, so this is actually the effective length that we are considering when we are talking of buckling failure. Okay, so KL actually is the effective length considered. So for the basic column strength assumption, letter C, This is with regard to buckling. The small deformation or deflection theory of ordinary bending is applicable, and shear may be neglected. Okay, so small deflection theory states that the effect of nonlinear deformation may be neglected, and shear, including torsion effect, are also neglected. So here, the torsion and the twisting is assumed not to occur during the bending behavior. So I have here a stress strain coupon, which is given in terms of the elastoplastic behavior. So this red here inhibits an elastic, perfectly plastic, okay, or simply an elastoplastic behavior. And you can see here that the blue line calls for the consideration of what you call a transition curve that produces some errors in the computation of the basic column strength. So I will discuss further what are the causes of this sudden drop of the modulus of plasticity involved. Okay, so this directly affects the slope of the modulus of elasticity. So if this is the slope, the initial slope of the modulus of elasticity, E, then this becomes now your tangent modulus of elasticity. Okay, so the fact that the slope of this decreases, the strength of the column also decreases. So we have to find out what really causes this drop on the value of your modulus of elasticity. So the part in which the drop of the elasticity happens is actually the inelastic stage or mode, wherein inelastic buckling failure may happen. Okay, so this is the failure mode that may happen, and this is actually happening on the inelastic range. So when we're talking of inelastic, we're just talking the range beyond the elastic range, okay, or simply the plastic range. So you can also say that this is now your beginning of your plastic behavior, and it explains what happens at the sigma epsilon transition curve. And for non-slender columns, it can buckle when some of their fibers are behaving inelastically, and that's the reason why there's what you call an inelastic buckling and an elastic buckling. So there are three theories that will explain to you how the basic column strength is achieved or is considered. The first one is the basic tangent modulus by Angesser, and this explains the column strength which remains straight up to the instant of failure, and the modulus of elasticity at failure is simply equivalent to the failure at, okay, the point in which the modulus of elasticity considered is tangent to the sigma epsilon curve. Okay, so this is now what I mean by the tangent modulus of elasticity. So there is a value of modulus of elasticity that failure will be initiated, and upon looking into the derivation of the Euler, it's the Euler buckling load, uh, which I discussed in a separate video, you will notice that the only difference between the two is that your E is considered the tangential modulus, or E tangential. Okay, so I discussed the derivation of this on the separate video. Okay, for the double modulus of Angasser, he simply separated the behavior of the part in which the fibers of the steel is behaving elastically, and that part in which the fibers are behaving inelastically. Okay, so it simply gives us an indication that this is the inelastic part and this is the elastic part. So how do we know it? No? So we just look into the value of your E here, which is 200,000 megapascal, or simply 29,000 ksi. And here, your E obviously is known, no? And it will be less than these two uh, values. Okay, so the integral sign here is simply the moment of inertia of the area into which the inelastic fibers behave, or sorry, the area into which the fibers behave inelastically. Okay, so this is simply the area of the inelastic fibers. Okay, and this is simply the area of the elastic fibers. And the formula for I'm sorry, it's not the area, but the moment of inertia. Okay, so this is simply the moment of inertia of the inelastic fibers, and this is the moment of inertia of the elastic fibers. Okay, so just take a look on your calculus that the moment of inertia is simply the integral of y squared, okay, dA. So you go back to your uh, or simply make a recollection of uh, your definition of moment of inertia in calculus. So for the third, okay, actually this is now the third theory, and this letter C, okay, the Shanley load or the Shanley strength actually resolves some inconsistencies in the two, but favored your tangent, basic tangent modulus as the more correct formula, since it was found out that your load for this particular concept is slightly greater than PCR, but for practical purposes, such increase in the capacity may be neglected, and hence the tangent modulus load is the one that's considered as the critical load into which the bending begins on the inelastic range. Okay, so this is now the inelastic. So for the common test results or the column test results, it is now generalized that the concept of Shanley uh, are the ones accepted, but still gives computed strength higher than test values such that the value of the basic tangent modulus uh, are now modified a little bit and taken into account by the formula for the ASD and LRFD, which is introduced by the AISC formulas. And the reasons for such adjustment are found to be caused by these factors, which are actually very evident, no, in the assumptions that was given earlier. Okay, so these are the basic, this is still the basic assumption. Initial crookedness of the member, accidental eccentricities, and restraint. Okay, so this is actually the first three assumptions also made initially on our column strength. Okay, here with regard to shape and condition. But there are two additional considerations that were placed just to qualify that the Shanley concept cannot be used, and the basic tangent modulus must be adjusted so that these are attributed to these two factors, which has something to do with what you call a local buckling effect, okay, which is based on plate stability analysis, and the residual stress, which is based on actual uh, test made, okay, uh, after the manufacturing process, uh, to come up with the value which will modify, okay, the equations needed in your column strength analysis. So for the local buckling, this will be separately treated, and for the residual stress, this explains why the sigma epsilon curve becomes nonlinear beyond the proportional limit. The stress that remains in a member after it has been formed into a finished product and will result from plastic deformation. So this has something to do with the manufacturing process. And several causes of residual stresses, which are actually or specifically stated here, the cooling process. Okay, so upon applying the heat, of course, we need to cool down the temperature, and this gives significant effect on the residual stress coming from hot rolled shapes. Cold bending cumbering needs also some temperature differences, inhibits some temperature differences, punching of holes and cutting operations, and also welding. No? So this has something to do with the temperature change, the temperature differences from the application of heat to the process of cooling down uh, to a normal temperature. Okay, so these are all contributory to the residual stress of your mem. Okay, so that's it for the introduction. We'll proceed with some column stability concepts on the next video. Thank you very much.